Okay, so welcome to the week 8 of the course Fundamentals of Micro and Nanofabrication. I am Udiptya, PMRF scholar from IIT Madras. So we'll be discussing the problems from the week 8 of the course. So okay, so the optic this course of week 8 was mostly pertaining to it was a continuation of the optical lithography that we studied, and it was the first was on mask technologies, like how to make the mask, and then it was on lithography process and some terms that we come across when we do lithography, and the third was on how to go on with enhancing the resolutions, and we saw some methods to do that, and then we then the two more lectures was on electron beam lithography. So it was mostly to use electron beams to write on the photoresist, and basically the pattern transfer, not a photoresist, electron resist, and some emerging lithography processes. So let's go to the questions now then. So so the problem one is from mask design. So you have to tell that a pellicle is a transparent protection over the mask, and it prevents distortions due to dust particles deposited on mask pipe. So you have to tell the mechanism of how pellicle is having this protection over the mask. So these are the options, and you can type the answers in the chat box, or maybe turn your mic on and tell us. So for those who are joining now, we are discussing on the protection by pellicle, which is a transparent protection over the mask used for photolithography purposes. So you have to tell how this pellicle is helping to prevent any contaminations from dust. So these are the options, and you have to tell which is the most ideal reason. Anybody? So we will discuss the answer then. Yeah. So you have a mask. Yeah. So it will have some portions of chrome and some. So this is the upper part is glass. It's the glass part, and these are chrome. Okay. So some parts will be these parts are opaque essentially, and the clear parts are so these are open. These are transparent parts. Light can enter through this, and light can't enter like from this. These are opaque portions. Okay. So what happens is that we put a transparent protection over it. Okay, and anything this is basically the pellicle. Okay, and this what it does is any dust contaminations, if it sits in it, it will sit in like here, and and we know that for a optical system the focal length is fixed, so we can have the focal length that is fixed. So it is made in such a way that the patterns are in focus. So we use some optical illumination optic, like focusing optics, and we focus it from the plane of the mask and not the plane of the pellicle. So whatever is available here, these are basically not focused, not completely focused in the not in focus of the our photoresist. So what happens is that we do not like the due to the dust, there is no any major contributions that can affect the pattern transfer on the our photoresist. So that is the B option. Yeah. So making dust particles out of focus and forming its image beyond image plane. So the image will be formed beyond the image plane, so it will be formed here. So that's the thing. And you can see if it's this pellicle is not there, it will be lying here and it is completely in focus. So anything distortion, it will be directly like it will directly be copied to the your resist material. So that's the thing. If any doubts, you can ask, and so you can stop me anytime, and I'll be happy to answer it. So okay, let's go to the next one now. So this is the plot of line width versus depth of focus is shown here. Okay, and x, y, z denote different source frequencies. So you have to choose which is the correct option. So like here you can consider this as a positive photoresist. So positive photoresist is something in which upon illumination it dissolves. Dissolves upon illumination, upon exposure. So okay, you can try. Anybody? Which can be the correct thing? If the questions are not clear, you can ask. I can help you with that. So like if you're confused about line, what is line width, it is something like if you want this is the photoresist, yeah, and so the length, basically the length is line width. So basically if you want to make such kind of structures, how will you make? You will have a mask set up for this, and it will have, because it is positive photoresist, you will have a like you will have a photoresist, you will have a mask like which will be opaque here in the middle part. So you will have this, and these will be transparent. So it is chrome, and these are no chrome. Nobody? Then we will go to the answer. So we know that when we add more energy in the case of positive photoresist, it should expose like like with more energy the exposure will increase. Okay, and as we expose more, it will dissolve more. So this line width is essentially will get smaller if we expose it more. Yeah. So with the highest energy, we will get the lowest line width. Yeah. So here the lowest line width is in the case of Z, and then the second is Y and X. So the increasing like the within like this is the inverse relation. Yeah, the line width decreases, so the this frequency should increase. Essentially the line width increases, line width will increase this way, so the depth so the frequency should be like this. Okay, so it essentially will be frequency will be Z, like with the Z, Y and X. So it should be none of this. Okay, I hope it is clear to you all. Yeah, if any doubts you can ask, no issue. Okay, we'll move to the next one then. So from the lecture we told that we will have 1:1 mapping of mask to wafer in a projection lithography system. Yeah, and this is called linear mapping. So but for this problem we have told that you have a mask mapping in a quadratic function. So essentially 1:1 is like you will have y equal to mx. Yeah, kind of mapping. So you can have y as the like the mask the mask length, and x as the what is on the line width of the wafer. And so here, but it is not like that. Essentially it is mostly linear mapping. For this problem we are telling that this mapping is quadratic function. Okay, so we have given some values, 200 nanometer to 100 nanometer. So 200 is essentially the mask size, and 100 is the what is transferred to the wafer. 450 to 150 and 800 to 200. So you have to tell so you want a line width of 300 nanometer. So what should be the size on the size of that what should be the size that is present in the mask? So the pattern size. So it's basically the pattern size. For 100 nanometer pattern you are using 200 nanometer on the mask. The pattern should be 200 nanometer of size in the mask. Same here, and similarly the relations are here, but for this 300 you have to tell what should be the feature size in the mask, is that you can get a 300 nanometer line width in the wafer, and the relation is quadratic function, unlike the linear one. So you can start with some general like general function of quadratic nature, and then you can put it. That might help you solve this question. Like here we have y equal to mx, such kind of things, and you can put as some general and try to fit it. Anybody is doing? Or should I proceed with the answer? Okay. So we will proceed with the answer. Yeah. So essentially, like we have a general kind of understanding of the linear mapping. We have some equation here, such that we can also, for quadratic equation, we can write that y equal to a x square. So a is some coefficient, and you can write like this here. So we can have a kind of table like on mask equal to y, and on the line width or wafer kind of, we'll put it as x. Okay, so for first value we have 200, and 100 is on the wafer. Similarly 450 and 150 is on the 800, 200, and you have to find what will be the 300. For 300 you have to find what is here. Okay, so what will you do is you can put essentially you can also use the full, like y equal to x square plus bx plus c, complete reaction equation also. So anyway, because three variables are there, so you can approach it. That will be a more general, more proper way. But here essentially we can do it anyways. But let's see if we can get the value. Yeah. So for y we'll put 200 and a and 100 square. First value we are doing. So essentially 2 I 100 0.02. Okay. Let's see if other values are also obtainable from them. 450. So 150 0.02 into 150 square, we should get 450. Yeah, that's 450. Another also you can check. So it's 200, 0.02 into 200, we should get 800. Okay, so essentially B and C are 0 already. So for 300 what to put? So y is unknown. Okay, we have to put 0.02 into 300 square. So essentially this will be the answer. So let me calculate. So on the mask side, you have to have features of 800 nanometer ranges, orders of 800 nanometer, 1800 nanometer, and that can give you line width of 300 nanometer. So this is the finally the answer. Okay. I hope it is understood by the students. Okay, we'll go to the next thing. So here we have that in projection lithography we have a source of 193 nanometer, 193 nanometer, and the numerical aperture of the projection optics is 1.2. So you have to suppose the required image contrast is 2, more than 2, so more than 2. Which all source shapes can be used to get a critical dimension of 60 nanometer. So this is just for like you can take help of the thing, but this may not directly give you the answer. So you have to calculate what you are getting, and depending on that we have to tell which of the sources is which of the following like geometrical sources of light is the ideal one. So directly from this thing you can take the help of the figure, but this may not directly tell you. This can only help you with the values of k maybe. So you can try. Essentially these source shapes have a big role to play in terms of the diffraction optics is concerned. So what kind of sources you are using, this can like determine how your image contrast will be there. So that's why that some terms like image contrast, the numerical aperture is something that is coming up, and you have to systematically link everything. So the formula essentially is given here, and to use put it in. Okay, should we discuss the answer then? Okay, let's go to the solution maybe then. Yeah. So first we will see what is given. We have an A of so wavelength is given 193, and A is given 1.2. Image contrast is more than 2, and CD is given. Okay, so we know that from the figure only we know that CD equal to K1 lambda by NA. So CD is 60, K1 193.2. So K1 value is 1.2 divided by 193, so it's 0.37. yeah. So now you can see that around 0.37, which is the ideal source for getting an image contrast of more than 2. So from the diagram you can see that 0.37 would lie, so this is 0.35, this is 4.5, and this 37 might be lying like nearly here. So here we see that dipole is the this region is dipole. Yeah, so you can see that we can from this thing we can depending on the K1 value we can see that dipole is the ideal source for using as a light source for this kind of for getting such specified projection lithography. Okay, so should we go to the next one then? Okay, let's proceed then. So we have this phase shift mask here. So this phase change mask uses optical path difference to get 180-degree phase shift to get a destructive interference, and this is done for having a enhancement in resolution. Yeah. So in this problem, glass layer is used over the mask with a trench. The trench is something that kind of looks like this, kind of a step like thing. To obtain a required phase difference with a source of 248 nanometer. So lambda is given as 240 nanometer. So you have to find the D1 depth, D1 that is given to obtain 180-degree phase difference for figure A. So the refractive index is given of glass is 1.5. Okay, and so uh, and now because of the mask was kept on a poor environment, the trench was fully contaminated. So in case B, the trench is fully contaminated with oil. So that oil is refractive index. That oil has refractive index of 1.3. So you have to and that D2 is also causing destructive interference. So you have to tell the ratio of D2 by D1. So you all can try, and we'll discuss the answer. So you have to you can recall like what was the past path difference that such kind of systems impart, optical path difference. If you can recall that thing, that system, and then you'll be able to do it efficiently. So you can refer to that thing and come up with the answer. Let's go to the solution then. I hope you all are done. Okay, so path phase difference is delta phi equal to 2 pi by n minus 1 lambda by d. So d is the path difference. So essentially the physical path that is there. So here in the first case, or case A, we have 2 pi into n is 1.5 minus 1, lambda is 248 into d1 equal to pi, because optical difference pi is taken. So pi can cancel, and you will get d1 is equal to 248 minus divided by 1.5 minus 1 is 0.5 into 2 is 240. So d1 essentially is 240 nanometer. For B, so it has the depth 2 is needed for destructive interference. So we know that it is given that for 180 degree phase shift is needed for destructive interference. So similarly it will also require phase difference of pi. So same equation we will put that here the n would be different. 2 into pi minus 1 d2 to 48. So it will be d2 equal to 248 by 1.3 minus 1 is 0.3 into 2 is 0.6. Essentially d2 by d1 is 248 by 0.6 divided by 248. So you will get, this will come down to 48 by 0.6. So you will get 10 by 6 as the answer. Okay. So this is the ratio between D2 and D1. Okay. So we can go to the next one. Yeah. Okay. So you have to tell in electron beam lithography which type of scattering primarily decides the resolution. So you have to choose all of the options that you think is correct. Anybody? Uh, should we discuss the answer then? Or you would like to try? Somebody wants to try? You can write it in the chat box, whatever options you feel is correct. Okay, so we will go to the answer then, yeah. So essentially, forward scattering is something that happens when the electrons go past inside the resist, and it scatters very little, like because it has very less. It like scatters in very small angles, so it does not have much of contribution in deciding the resolution. And secondary scattering is like the primary electron coming, and it knocks off electrons from the like the atoms present, and it knocks off, and that atoms then spreads and causes the further collisions. So secondary scattering is therefore one of the important thing that has uh, that can decide the resolution, because it has like it is a elastic scattering, and it has much energy to knock off the other electrons also, to also affect the resolution. And the backward scattering is it hits and it like it like and it happens at much higher angle, so it will hit the atoms and it will go back. And so it also has a higher energy, and it can also spread at very high angles, so it also has a role in playing in the resolution. So it also determines the resolution of the electron beam lithography. So B and C is the correct ones which can decide your resolution. So, and the last option is elastically scattered electrons that causes photon emission. So as we are using electron resist, so photon emissions do not have much of the contribution, and they are like, they would not affect much of the resolution. Okay. So it's primarily the secondary scattering or the backward scattering that matters the most. Okay. So this is the last one. It is kind of may not be fully something that has been in your past physics courses or something, but not directly think, but this will help us understand how this electron beam lithography process and what are the challenges in it. So in this problem we calculate some numbers to increase the understanding. Okay, so why charging of wafer during electron beam lithography is a problem. So we have to just to get an understanding of that, we have put this question. So considering that the wafer has a top layer of silicon dioxide and is saturated with negative charge. So silicon oxide, essentially dioxide will essentially have a negative charge, and we have to assume that the wafer is an infinite sheet of charge. Okay, and the surface charge density is given. So we have to find the energy. Okay, you can also put it in terms of like the standard terms, and we can then like surface density you can put as sigma maybe. So sigma equal to, so you can also know it this term is also okay. Like if you on the denotions also, if you solve it is okay, it is acceptable. And you have to find the energy of the electron required to be launched at a height of 10 centimeter to reach the vapor. So you have to essentially tell how much energy, like because electron is also negatively charged and the surface is also negatively charged, you have to tell what energy it has to be, it needs to be possessed, such it needs to be accelerated such that it can reach the wafer. And so this essentially will tell us how like regarding the issues of charging or wafer. And this is only one factor here, and a lot of the factors are there in them, so it is just a simplified model which will help us understand it. So you all can try it. You may here start with some basic what you might have learnt in your high school physics, or like what is the electric field that is felt from an infinite sheet of charged. So that way you can start. I hope you all are trying. If you have any doubts, you can ask, like how you are approaching. So essentially, you can keep it in the terms, standard terms also. No need to solve it completely. you can report it in the equation form, and that will be enough. Just have to put the values only, so not an issue with that. Standard T notions will also work. Should we go to the answer, or you are still trying? So just to give you some like path, like when we consider a infinite sheet of charge, which is kind of negatively or positively charged, it doesn't matter actually. So the electric field that is felt at a distance, that is sigma by 2 epsilon naught. Okay, and for infinite sheet of charge, obviously it is not infinite. Just for infinite sheet of charge, if you consider it, it is independent of the like the distance. It is from the distance of the sheet. Essentially, the height of 10 centimeter is something you can neglect, and therefore you can proceed. So in this problem, this is kind of a model, but we have our own kind of conceptions that we have taken, and we have built the system. A lot of factors that in real world a lot of factors are there. So like real world simulations or modeling is quite difficult from what we are doing now. Then maybe we can start with the question here, solution. So we have so now we have to check what is the force that we have this electron, which is used for this electron beam, it is experiencing. Essentially it is the E into the charge of the electron multiplied with the electric field. So this is the force that the electron is facing. So electron charge is a known category, is a known quantity, and you will write the sigma by 2 epsilon naught. Yeah, okay. And epsilon naught is also a constant. So now this will be equal to the energy you need to provide such that it reaches the surface. So this will be the energy. So this much energy if you provide, so it will be reaching the surface of the wave. Okay. So that will be the solution of this. You can put the values here, and you will get the correct option answer. This is a numerical type problem. So that's all for today, and we shall close the meeting. If anybody has doubts, they can stay back, and others are free to leave. I will be waiting for another 5 minutes, and then we can close the session. Okay. Thank you, and we shall meet in the next week, same time, with week 9 discussions. Thank you.